today we'll move shift gears and move to what is called mid-level vision. Okay, so until now what we saw was deep networks in the first phase of this course. Then that was followed by low-level vision, where we saw about edge detection, feature detection, and all that. And then we moved to a geometry, right, where we saw single view, two view, multi-view geometry. The next in line is mid-level vision. This mid-level and high level are not as big as the other ones. And mid-level vision, in which the tracking part, right, that comes in mid-level vision, I'll combine it with YOLO when I teach YOLO for high-level vision. So right now the first topic, right, that we'll focus on under mid-level vision is what is called optical flow. Okay, and I'll actually explain along the way what we mean by this. Optical flow is, by definition, is the apparent motion of brightness patterns in the image. Brightness patterns in the image. Okay, now this the use of apparent, right, comes for actually a reason. Now this optical flow, right, I have to just pull out this slide. The thing is, right, see what we actually mean by this optical flow is that, right, it comes in when there is motion, right. When there is motion, it could be just object motion, it could be camera motion, it could be a relative motion between the object and the camera, both could be moving or whatever. But then motion is such a strong cue, right, that you cannot actually afford to see, right, neglect it. In fact, many a time motion is the strongest cue in a way. I'll show you some examples. And therefore, right, when you see what you mean by optical flow is that right, we are kind of no longer talking about one frame now. We're talking about frames that are varying with time, right. So you have something like a video, for example, right, where you have a successive bunch of frames, right, which you're watching. And when you're watching this frame, right, so what we call as spatio-temporal information, right. I mean, normally when you have just image, you're talking about spatial information alone, right. Now you're talking about what is called the spatio-temporal data. So the spatio-temporal data, right. So what we are saying is, if you're looking at this image and if you can analyze what is going on in terms of the variation of the brightness patterns, that can tell you a lot about what is happening in the scene. Right. Till now we weren't so focused on object motion and so on, right. I mean, we were kind of looking at more or less static situations and so on. But now the next escalation, in a sense, comes when you want to look at brightness patterns that are varying. Now, when these brightness patterns vary, right, I mean, typically look at a scene, right, where there is an object, right, and the camera is imaging this object and the object is moving. Now, the motion of the object itself, right, when it is moving, that's called scene flow. Okay, that's called, I mean, as opposed to this optical flow. Okay, that's called scene flow. And this actually refers to, or you can call it scene motion. This refers to 3D velocities of scene points. Okay, so it's like the actual motion of points in actually a 3D world. Okay, that's what we mean by scene flow. Then from the scene flow, right, when a camera is imaging through a perspective, right, a projection equation, then what you get is actually a motion field, right. I mean, this is what gets transferred to the camera, right, because we know that we can calculate where the XY coordinates are, and as the object is moving, you get a motion field, right, which is like saying where the XY points going. And the motion field, right, this is the 2D projection. This is the 2D projection. Projection of the physical motion of points, of the physical movement of points in the 3D world. So this is a 3D projection on the image plane, of course, on the image plane of the physical movement of 3D points in the world. Now, unfortunately, right, this is what we want actually, right. This is the motion field. I mean, this is what will tell you what object is moving, which direction, and where is it going, and so on. But what you observe is not the motion field, right. This is not observable. We cannot observe it. We don't observe it actually in a camera. What we observe is the actually, right, intensity, right, the brightness pattern, as it is called. So, what we see is just is intensity in the image, right. We do not get to see the motion field directly, but what we see are actually intensities. And the idea is that these intensities, right, in turn should help us compute the motion field. Okay, so, but then what we observe, however, right, what we observe are actually intensities. And the idea is to analyze these intensities in order to be able to make inferences about the motion field, right, which in turn can probably tell you something about the scene flow and so on, right. And what we observe are actually, right, intensities. Then so to say, so right, so what this is effectively means is that for example, right, so what you are sort of saying is that based upon the optical flow, right, I want to be able to say within an image, right, by how much has a point moved when you go from one frame to another, right, how much is, right, let us say at every point moved, in the sense that you want a velocity component which will be one along x direction, one along y direction, in order to be able to tell where every point is going, right. I mean, you are kind of looking at the velocity of every pixel now, right. That is what you mean by the kind of motion field, and that you are trying to infer based upon the optical flow, which is simply the illumination, right, that you actually see. Okay. And theoretically, I mean ideally, right, not I mean theoretically, I mean ideally, right, you would want the optical flow, that means the movement of the patterns, ideally, right, you would want optical flow or the motion of the brightness patterns, you would want the optical flow to correspond to the motion field, right. But in reality, what happens is there are cases, right, when it is not true, in the sense that you may have a motion field, but then you do not see any optical flow, and you can have optical flow, but then, right, there may not be a motion field at all. Okay, but then in most cases, right, it does work. I mean, in the sense that this sort of a correspondence is true, thankfully, right. In most cases, it is true, but there are exceptions where, let us say, such a thing, right, may not be true. That is why we say apparent motion. Okay, I mean, it does not always represent the motion field, but in most cases it does. Okay, so in a sense, right, what I think, right, we can say is that, right, we can say that, but okay, but in most cases, most situations, in most situations, the optical flow corresponds to the motion field, corresponds to the motion field. Okay, so in a sense, right, it works in most cases, and that is the reason why there is so much interest in that. But to just, right, give you an idea about what the optical flow is and so on, right, let us just kind of go to the slides, and we will kind of look at, what might be the use of having, what might be the use of analyzing a spatio-temporal volume, right, so to say, in order to make, right, inferences. So one is visual motion, right. So when you see this visual motion, it can be due to various reasons. It can be camera instability, it can even be camera motion for that matter, it can be a jitter or whatever. This causes visual motion. And visual motion actually, so it could also be because, right, some object is moving there. I mean, right, so what we have here is not the whole set of things that can actually cover. A few are listed here, but then you can think about, right, visual motion can occur, right, due to object motion, that most of the times, right, that is the case, and it kind of indicates a dynamics in the scene, right. When you say a dynamic scene, right, you really mean that some things are moving independently of the others. I mean, that is when you mean it is a dynamic scene. For example, right, just because an image is changing over time, it does not mean that it is actually a dynamic scene. For example, right, I could have a perfectly static scene, but I just move my camera. So if you look at all my images, right, they are not the same. But then, right, that does not mean that my scene is actually dynamic. Scene is not dynamic, the camera is moving, right, that does not make the scene dynamic. So when you say that a scene is dynamic, you really mean that there is one or more objects there, and there is a background perhaps, right, and there is more than one object perhaps there, which is going through some independent motion, or which are going through some independent motion, right. So you have like moving objects, behavior, and most of the time you see this, right, somebody is you could have a game, right, where let us say, right, the people are playing, the camera could be static, but then there is so much activity going on, right, and you want to make inferences. trajectories, right, object tracking. So much you can do if you knew what was going on, right, if you could actually predict, I mean if you could analyze that that movement of the brightness pattern and be able to tell certain things. And it's also nice that this also includes parallax, in the sense that something being in the front will move something, let's say even if it's a static scene and if you're moving a camera, right, there's going to be a motion pattern, right, because like I said, it's a relative motion. And at that time, right, you will notice that things in the front would have moved faster than things in the back, which is the parallax effect again, which means that right, on the image plane, when you see this motion of patterns, right, you sort of tend to know that some things moved faster than others, and therefore and because the camera translated uniformly for everybody, right, so that sort of tells that something is in the front and something is in the back. That's the parallax skew. In fact, right, going a little backwards, right, the Tomasi-Canade factorization method, right, that we did is actually one kind of optical flow. If you kind of recollect, right, we had an observation matrix, right. What is that observation matrix? That just had the U and V in it, right, across all the frames. If you guys recollect, just a few classes before, right, we had a motion matrix that had only U's and V's in it, right. We had like various feature points coming along the column and then across the frames, right. There was a correspondence. So what is that really, right? I mean, so it's like saying it's like an optical flow. You're telling where this point went, right? Where this point went, where that point went. That's exactly what you're trying to indicate, and that led us to compute the structure of the scene, right? You could say what was the structure of the scene. So in that sense, right, we have already utilized it, even though we didn't sort of explicitly talk about it as being optical flow or anything. But yeah, I mean, right, so optical flow is something that is not new to you in a sense, right? We have already used it, but then used it in a sort of an indirect way. Okay, now think about this, right? So sometimes motion is a foremost cue. So you actually, right, there are even GIFs and all where you see a small motion, and it's the motion only, right, that actually tells you that there is something sitting there. Otherwise, the thing is so very camouflaged that you can't make out that there is a different object sitting there. So which means that motion is sometimes a foremost cue. And here is what you have, right? In a sense, you have a spatio-temporal volume, right? And you sort of represent it as I x y comma t, right? Until now, we are only talking about I of x comma y. Now we introduced a third sort of a dimension, which is the time, right? Like I said, this is now spatio-temporal data. This is like a video. And optical flow is typically between kind of, right, two frames, and then you can do it successively. So the motion field versus optical flow, right? So think of a situation. Do I have like that? Okay, yeah, I don't have the slide for that. But then think about the sphere, right, which is there, which is kind of uniform, right, in the sense that the sphere, it has the same sort of reflectivity wherever you go. The material is exactly the same. Okay, the sphere. Now, if I had the sphere, and let's say right, of the sphere, and there is some kind of a lighting, right, from there, which is where you see that there is, on the one hand there is some shadow, and on the other hand there is some more brightness, right. That's because you can think of this as the light being somewhere coming from there, right. That's why that portion is more illuminated. Now, if you actually rotate the sphere now, which is like an actual scene flow, there is actually a scene flow, right, that is object is actually rotating. What will you observe in the right images? If I capture such a video, what will I see? You will see exactly the same picture, right? All through, you will get the same picture at all, because even though the object is moving, right? So what this means is that there is a motion field. Actually, there is a 3D motion, but then on the image plane, right, you don't see a change in the intensity at all. Right. So in that sense, right, this is a situation where there is a motion. Like I told you, right, it's not always true that one means the other. And as I said earlier, right, so what you can observe is only the optical flow. So does the optical flow, right, imply the motion field or not? Right, need not always. So in this example, what have we got? We've got motion field, but there is no optical flow. But now, suppose I kept the object still, and suppose I move the camera. Right. Suppose I take a video by kind of moving the moving the light source. I had a light source here. Now suppose I move the light source. Okay. Now there is no motion really, right? Because this guy is still, my camera is still watching from here, but I'm kind of moving the light source. Then what will happen? You will see that this brightness that you're seeing on one side of the sphere will gradually shift, and then, right, it will come out to this side. Now, if such a video, if I capture, will there be optical flow? There will be optical flow, because it will look like right, there was a pattern of motion, but then really, right, there was no motion, right, in the scene, there is no scene flow, the object never moved, right. So in that sense, there are these extreme situations where there is no motion field, but then there is optical flow, or there is no optical flow, but there is motion field. But then in most cases, right, it works well. Okay, so just because there are some extreme cases where right, things don't work out, it doesn't mean that we should simply throw it away. Okay. Then why is optical flow useful? Like I said, at depth, 3D reconstruction, that is what I told you just now, which is this one example could be this Lucas Canidae. Then motion kind of a detection, right, that helps you not just track, right, I mean you can even do action recognition and all, right, people do based upon how well you can track different body parts. You can say what somebody is doing, what his action is, then compression, so many things, right, mosaics, right. Again, I mean mosaic and all is all about right, I mean having an optical flow and more, right, a lot more that you can do. Okay, maybe some examples will come along the way. And as I said, right, so if you see these see the small little things, right, and so at every sort of a pixel, right, that's actually a motion vector, right. So the sense that, right, by optical flow, what you mean is at every pixel you want to say how this pixel moved from here onto this next frame, which means that you have to see of course 2 frames, right, and you're trying to say how it moved, and the length of this vector, right, will mean at at what sort of rate of velocity or at what speed, right, it moved, and then the orientation, right, will tell you as to, right, which way it's moving. So in a sense, right, typically they would show it like this at a particular location, right, you will have a vector that looks like that. So this length tells you at what speed is this guy moving, and the orientation tells you, right, right, which way is it going. And you can actually do it at let's say, right, every pixel, and that in a sense gives you a notion of what is moving and what is not, and so on. And that's a big Q, by the way, okay, as you will see further. So here are some examples, right, that you see. Now the first example, right, I mean where you see that if you look at the brightness patterns, right, they all seem to be coming inside, right, moving inside. What would that be? It will so suppose it's just you are just doing a camera lens adjustment, right. So it will be like zoom out, right, because when you zoom out, I mean all these patterns will start to shrink and then, right, come towards the center. The opposite will be zoom in, right, when you kind of change the camera focal length and then you get a zoom in. So that's like, right, expanding, and that will create motion patterns to go out. Then if you have a camera that's panning from right to left, right, you will get actually motion vectors like this, and if you notice, right, they all are of the same length, right, that actually tells you a lot about the scene. Okay, we will see, right, down the line. There is one more example coming that which will make it even more clear. Then you can have a camera, right, instead of let's say this kind of what do you call a zoom in, right, you could have a forward motion, right, which is by the way, right, I mean changing the focus is not really a depth cue. Okay, moving is actually a depth cue. Okay, so even though these patterns and all may look alike, right, oh there also everything is going out, here also things are going out, so are the two equivalent and all, right, we don't make those conclusions, but we know that these vectors, right, are if you kind of find how those vectors are moving, so when you actually move forward, right, you will get actually the motion to be as shown there. Rotation, if you happen to be rotating about a point, right, then you can see that if you're rotating about that point, then there is no optical flow there because that guy just remains stationary. But then as you go around, right, you see kind of more and more motion, especially at the boundary for the same rotation, right, you will get a lot more motion at the boundary, right, which you can imagine, right. A point, I mean it's like this, right, I mean it's like having a vector, right, like that, and if you see, right, for the same angle, okay, a point here, right, can only move so much, whereas a point here has to move, right, that much more, right. That's why in a rotation you see that the optical vectors, right, will be longer in length as you go outwards to the boundary, and of course they kind of they also indicate a direction, right, which sort of indicates that there is a kind of rotational motion going on. Then the next case is that of a horizontal translation, right. So here you see that this is something similar to this, but then, right, this one, right, this one, the interesting thing is, right, I mean so in this case, suppose I asked you, right, what to say, yeah. So is this a camera motion or is this like multiple objects moving? This situation. How would you make that out? Just by looking at the optical flow, right? That's the optical flow. What would you conclude? Is it like a dynamic scene, the camera is static, or is it like the camera is moving and there are probably multiple objects, some of them moving and some of them not, or what would you say? Actually, right, this is a case where the camera is static. Okay, the camera is static, and there is an object behind which is moving, and there is an object in the front which is moving, and the behind object is like, it looks like that's one. So you can imagine that, you know, that's like probably it's like one big object that's moving together in a sort of a cohesive way. That's why all its optical flow vectors are having the same length and all that. Whereas you see that there is a larger optical vector in the front, right, which means that there is an independent object in the front of the camera which is moving. Now, why I said this is not camera motion is because, right, if 1 minute, what did I 1 minute, right, let me just think about it. So, if you had wait a minute, right. So, if you had no camera motion, oh, okay, this is just the opposite way. No, okay, what this actually means is that the camera is actually moving, okay, because the camera is moving, right. I mean, you get a kind of motion in the background, and because there is an object in the front, right, it's moving faster. If there was no camera motion, then what would happen? The background would have actually zero this one velocity. Well, the first one that I told is also not incorrect. I mean, you can think of a situation where there is some big object that's moving in the back, but the simplest thing that you can sort of relate it to is, if the background, right, everything looks like zero optical flow, that actually means that the camera is static, and therefore you don't see any motion in the background, and probably there is this one object that's moving in the front which will kind of create an optical flow. Okay, because there is motion in the background, right, this can be actually, you know, it's not wrong what I said, right. What it means is that it could be that the camera is moving and therefore the background seems to have a motion, or it could be that the camera is static but there is a background object which is actually moving, right. I mean, all three things can occur. Is that okay? I mean, right, if you think about it, I mean, all three can occur. Okay, they are all valid. So, for example, right, I mean, you know, so here is a zero velocity, right. So, it means that, you know, nothing is moving in the scene, and then, right, if you add something more, no, in this case, right, yeah, here is where you would conclude for sure something. In this case, you can conclude for sure that the camera is static, because the background is all having zero velocity, right. I mean, you can think of a more complex situation, but I don't want to kind of enter. What is that complex situation? Exactly, yeah, that also can happen, right. I mean, what he said is correct, right. It can also happen that the background and the camera are exactly moving in the same with the same velocity, in which case it looks like the background is always static, but there is something else in the front which will have a different optical flow. But yeah, but when actually, right, that's why this optical thing is a big, you know, there is a big psychological study on optical illusions, right, you must have seen. Therefore, it's not true that whatever you see can make, you know, very, you know, clean inferences, but most of the time, yes, right, you will be able to tell what's going on. Okay, so here, right, it's like there is an object here which is actually right, moving to the right. Okay, that's an independent object that's moving to the right, and right here is a case where the object is moving directly, right, towards the camera, right, which is the reason why you have this outward vectors, right, going from that point, whereas the background and all, it is still having kind of a zero velocity, right. So, you can have all these situations. Now, where can you use it, right? I mean, it's a big queue. Now, here, right, nothing is moving in the scene, but then your camera, let's say, has moved, and you capture multiple frames, right. Then the optical flow can help you segment this image, right, because what it will tell is this tree in the front will move more, and therefore it will have a different optical vector and the optical flow, and then right, the kind of the house in the background, right, it is some other depth, these guys are at some other depth, right. Therefore, you can see that, you know, based upon the optical flow itself, we can segment this image, right, which is like a big queue now. All that right, you did was just to take the camera and move. And then, right, you can also segment, right, objects based upon their optical flow, because, you know, because if it's a rigid object, right, then the whole segment will have the same optical flow. You can kind of group them together. You can group, you know, a different bunch of objects together. You can group a different bunch of objects having similar optical flow together. I mean, that way, right, you also know that there is probably multiple moving objects, right, in the scene and so on. Then 3D structure we already saw, right. I mean, you know, you can do something like structure from motion. You can actually do something like super resolution and all, right. I mean, I don't want to actually, right, enter into this. Then recognizing events, right, I told you already. Okay, now let's kind of, right, do the math now. Okay, this is fine. Now, how do you even right, go about right, I mean, right, analyzing optical flow. Now, the way, right, it works is as follows.